Alright, so next up are properties of the dot product. So from previously, we noted that A dot B is equal to the magnitude of A, magnitude of B, cosine theta, where theta is the angle between vectors A and B when they are arranged tail to tail. And we also saw that A dot B is equal to A1B1 plus A2B2 plus A3B3, where A is equal to A1, A2, A3, and B is equal to B1, B2, B3. So we're going to prove the commutative property of the dot product using algebraic vectors. So to start our proof, we're going to let A equal A1, A2, A3, and B equal B1, B2, B3. Next, we're going to pick a side. So let's say we take the right side. And we see that the right side is equal to B dot A. Using the definition of the dot product, so that is equal to B1, A1 plus B2, A2 plus B3, A3. And since A times B is the same as B times A, we end up with A1, B1 plus A2, B2 plus A3, B3, which you note is the dot product A dot B. And we've proven that the left side is equal to the right side. So the commutative property holds for the dot product. Next up is the distributive property. If I have A dotted with B plus C, I can distribute that dot into the brackets, and I should have A dot B plus A dot C. So to start the proof, we're going to let vector A equal A1, A2, A3, vector B equal B1, B2, B3, and vector C equals C1, C2, C3. In this example, I'm going to take the left side. So the left side is A dot B plus C, which equals A1, A2, A3, dotted with B plus C. So that's going to be B1 plus C1, B2 plus C2, and B3 plus C3. Next, using our dot product, and remember that means I'm going to multiply the x with the x, I'm going to multiply the y with the y, and I'm going to multiply the z with the z. So I end up with A1 times B1 plus C1 plus A2 times B2 plus C2 plus A3 times B3 plus C3. Next, we just distribute. So I have A1 B1 plus A1 C1 plus A2 B2 plus A2 C2 plus A3 B3 plus A3 C3. Next, I'm going to group these into two different groups. So I'm going to take the A's and B's, and then I'm going to group the AC values. So what I have in my first grouping is A1 B1 plus A2 B2 plus A3 B3. And then I have A1 C1 plus A2 C2 plus A3 C3. And notice that the first bracket there is the dot product A dot B, and the second bracket is the dot product A dot C. So now we've shown that the left side is equal to the right side. So therefore the distributive property does hold for the dot product. So again, on your own, I'd like you to prove the magnitudes property and the associative property. And to prove them, I'd like you to use the following components for your vectors, A and B. And once you've proven those two, I'd like you to use the distributive property, commutative property, and magnitudes property to prove the following. Alright, one example for today. Determine the components of a vector that is perpendicular to both A and B. And again, keyword is perpendicular. And if I want a vector that's perpendicular to both A and B, we know that the dot product of two perpendicular vectors is equal to 0. So we're going to start off by saying let n, this vector that's perpendicular to both a and b, is equal to x, y, and z. We also note, since it's perpendicular, that a dot n must equal 0 and b dot n must equal 0. So for a, I have negative 1, 4, and 7. And remember, for n, I have x, y, and z. So I'm going to dot those two vectors. For b, I have 2, 3, and 5. And again, for n, I have x, y, and z. If I dot these vectors, I get negative x plus 4y plus 7z is equal to 0. And I get 2x plus 3y plus 5z is equal to 0. So notice I have two equations and three unknowns. And I have more unknowns than equations. So this tells me that there must be an infinite set of solutions. So let's talk about why this is true. So let's draw the two vectors that I have here, a and b. So let's say here's a and here's b. And I want to find a vector that's perpendicular to both a and b. So let's draw that here. So it's perpendicular to b, but it's also perpendicular to a. So there's one picture of one, but why couldn't it be pointing in the opposite direction? So there'd be another one. It could be twice as long. It could be half as long. So you can see there are going to be infinite vectors that are collinear to that green vector there. Alright, so how do we deal with that? Well, what we do is we just restrict a variable. Since there are an infinite set of vectors, we're going to take one of the variables and let them equal a value. What I recommend is that you don't choose 0. So for this one, I'm going to say let x equal 1. So I'm going to say that this vector that's perpendicular to a and b is going in the x direction 1 unit. So then we have this. If we take our equation here, we'll call it equation 1, and we'll call this equation 2. If we take equation 1, that means I have negative 1 plus 4y plus 7z is equal to 0. If I take equation 2 and sub in 1 for x, I get 2 plus 3y plus 5z is equal to 0. I'm going to call these equations 3 and 4. Now I have two equations and two unknowns I can solve using substitution or elimination. So take a moment now, decide to use substitution or elimination, and then come back and check your work. And you see, once you're complete, you end up with x equals 1, z equals 11, and y equals negative 19. So this tells us that the vector that's perpendicular to both a and b, vector n, is equal to 1, negative 19, and 11. And again, there are infinite answers to this. This is one of the possible solutions. As a side note, if you're interested, if we let y equal 1, I ended up with the following vector: negative 1 over 19, 1, and negative 11 over 19. And if I let z equal 1, I ended up with the following vector. I ended up with 1 over 11, negative 19 over 11, and 1. Tell me, what do you notice about these three vectors? If you don't see anything, then please let me know, and I'll try to guide you through this. Alright, so from your book, I recommend the following questions. Again, on your own, using the following vectors, prove the magnitudes property and the associative property. And then using the distributive, commutative, and magnitudes property, prove the distributive property part 2. Good luck.